Well, here's my little drawing of what happens in this problem. First we have big Brutus, and I think he's moving this way, and here's little Fred moving that way. And so then they crash into each other. And now they're kind of stuck together and moving in the direction that Brutus was originally moving. And they hit the ground and they start to slide. Then, after sliding some distance, they stop. So that's my diagram of what happened. Now, in between this part and that part, in between here and here, what we have is conservation of momentum. Because there's no net external force, we just have the two motions of the two players combining to make one total motion. That's conservation of momentum. From here to here, what we have happening is that an external force is taking away the velocity. And the way that's easiest to analyze that is the work kinetic energy theorem. So that's how we're going to get there. So let's start from the beginning because that's where we have the most information. We're going to do conservation of momentum. So we have the chart. And we have before and after. We have Brutus and Fred. And so we just fill out that chart. Mass of Brutus, velocity of Brutus. Fred is going to the left, so I'll make him negative, minus mass of Fred, velocity of Fred. Afterwards, we have mass of Brutus times the final velocity that will be the same for both of them because they move together, and mass of Fred times the final velocity, which gives us this equation. Mass of Brutus, velocity of Brutus, minus mass of Fred, velocity of Fred, equals mass of Brutus plus mass of Fred times the final velocity. And we can find that final velocity. Next, we're going to go over here and do the work kinetic energy theorem. The work kinetic energy theorem says that work equals the change in kinetic energy, which means for us that that's going to be equal to the minus the initial kinetic energy because the final kinetic energy up here is 0. So the final kinetic energy is going to be negative, because of that negative sign, 1/2 the mass of what's moving, which is mass of Brutus plus mass of Fred, times the initial velocity before the work started. So that would be this velocity here, v squared. And that has to be equal to the work. And the work is always FD cosine theta. And so the force that's working in this part is going to be friction, and friction goes this way as they move that way. So that means that the angle that we're talking about is 180. So this is going to be 180. The distance is this distance that we're looking for, and the force is friction. So friction, we know, is mu times the normal force, and the normal force in this situation is just going to be mass times gravity. So that means the friction's equal to mu mg. I put that all together and I find out that mu mg d cosine 180 is our work, and the m in this situation is going to be the mass of what that friction's acting on, which is Fred and Brutus. Cosine of 180 is -1, so I'll put that together and I get minus mu mass of Brutus plus mass of Fred GD equals, bringing this guy down now, minus 1/2 mass of Brutus plus mass of Fred times the velocity squared. So now the masses are going to cancel out, the minus signs are going to cancel out, and we'll just have mu GD equals 1/2 v squared, and we should easily be able to calculate D from there.